Okay, here we go with our Cfe Physics and higher graph analysis. Now, the key point about these questions is you've got to analyze some data, and then you might be asked to mess with a straight line graph. Now, so it's very important that you know that once you've drawn your graph, if it's a straight line graph, you might be asked to do some certain things with it. If it's not a straight line graph, then you're kind of tested on the graphing skills and you're asked to do something probably with data from the table, substituting into an equation or something a bit more friendly. So inevitably it would be an equation that you view as not being very friendly. Now, this all builds on straight line graphs having the equation y equals mx plus c. And I'm assuming you've done this in maths for years and years and years. And so I'm suggesting to you that here's my first graph, the black line, that is y equals mx. Now, in this case, because it passes through the origin, there's no y-intercept. And I'm assuming, because the maths people have taught you for so many years so successfully, that you know that whatever you call that, whether it's m or whatever that letter is in front of the x, that's the gradient. And that this c value is the y-axis intercept. Now, there are a few things to consider here. First of all, that adding numbers to this just slides the graph up the y-axis. So if you have so if this is y equals mx, I could have y equals mx plus 1, y equals mx plus 2, y equals mx plus 3, y equals mx plus 4, and I just 5, 6, 7, 8, and I just slide a parallel line up there. Because the gradient is the same for all these lines, because they've all got m as their gradient. Now, if you don't see a y-intercept, it doesn't mean that there isn't one. It could just be that you're given a graph like this. So if you look at the red line, and your graph was, these are all x values, of course. If you've only got data that fills this line here, the fact that you can then draw in a straight line, you know you have a negative y-intercept. Although it might not be obvious, if you've got an intercept on the x-axis, that kind of implies that you must have a negative intercept on the y-axis. Hopefully that's obvious just by looking at it. So we're going to move on and look at some examples of things that you have and how things are going to be set out for you. I'm going to try and do it sequentially. So what I decided to do was, imagine we've got data, which is about, our question is about this graph. So our question is about potential energies and heights. And so you'd probably be given data in the question that would be sort of EP data and H data with appropriate units. And you'd be asked to draw a graph, and you might have a graph like this. Now, this equation does not have a term, does not have a plus, and does not have that term. So its y-intercept should be 0. So if when you plot the points and you draw the line, you have a y-intercept, that immediately makes you think, hold on a second, I've got a y-intercept here. That's a bit strange. The equation shouldn't have a y-intercept because there isn't a plus something in the equation. That kind of means something went wrong. In fact, maybe the height data went wrong. And maybe the person measuring the heights wrote down all the heights a little bit too long or too high. And so instead of having the graph in the right place here, what's happened now is all the heights have been giving a few centimeters extra, and so the graph has been pushed up. Now, this is what we would call a systemic problem with the experiment or with one of the measurements in the experiment. Okay? This is a systemic issue with the experiment, that something's wrong with all these H values because they all sit nicely and obey some sort of direct proportion, but some sort of proportionality, but it's not direct because the line doesn't go through the origin. So we have a systemic problem with the experiment or with one measurement, and in that case, that's this H measurement. Okay, so if all the height measurements were 5 centimeters too big, we would end up with the correct graph pushed up the y-axis like this. So if you see a graph that should go through the origin and it's not going through the origin, that says systemic problem because, of course, if you substituted 5 off all, then you'd end up redrawing that graph with your h-axis. Now, if you made a subtraction of this systematic error from your data, you end up redrawing that graph with a line going through the origin, and it would look like the proper graph. So your axis, your graph would look something like that. Okay, so if you made a subtraction from the data, your graph would then look like that. It would look like the proper graph, and because there should be no y-intercept. Systemic error if your line's displaced. Next step, what else can you do with this? What else can you do? So let's look about using the gradient. Okay, so we're back on the same experiment. We're graphing potential energy against height. Now, one thing is, you've got to draw a line of best fit, and I'm not particularly proud of this one because I reckon that point could have been on it probably if I'd just drawn it a tiny bit, if I just rotated my line a tiny bit up there. The other thing is, you won't be given point. If you are given points, you shouldn't draw lines of best fits beyond the points. So if your points end there, end your line of best fit there. Don't do your line of best fit beyond the point, because that kind of looks like you're extrapolating into a distant future beyond the data. So if we don't know anything about the EP beyond this maximum value of h, so I can't really carry the line on and say, I know that this is a straight line forever, because I've got no data to support it. Definitely a no-no. Okay, let's look at what else we can do with these graphs. So I'm not talking about the fact that it's not right. I'm going to just talk about the gradient. So I've drawn the graph as above for this. But what's important is that I can map this to y equals mx plus c and say, okay, the y-axis that I've been taught to use, the y-axis, that's my EP. This has got to be a y equals mx, but of course, there is nothing here. There is no plus and then a something. So essentially, I know that c equals 0. C doesn't exist in this case. And that's why the straight line should be going through the origin. Secondly, it's a bit awkward in that the standard maths form of m could be confused in this one because we know that that's basically just a gradient. M is the gradient. And so in our case, h is the x, EP is the y. So all this is the gradient. So if I was asked, say, my gradient is mg in this experiment. Okay, and so this is an absolutely vital step, that I can then measure the gradient here and go, okay, going across. Now it's very important that you use more than half of the line. So make the biggest triangle that you can practically make on the graph. And remember that it's the up divided by the across. Okay, I know a lot of you use this y2 minus y1 over blah, 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 but I always think it's the up bit divided by the across bit. And it's the up divided by the across, and be careful with the units. So you'll be going to take the units off the axis. So if my height was in meters and my potential energy was in joules, my gradient would be measured in joules per meter, because it would be joules divided by meters. Anyway, that's probably not going to be important. We're just going to take the value. So in this case, when I work out the gradient, I know that the whole gradient equals mg, because I've got that from my equation here. All of this becomes the m term in my y equals mx plus c. Having done that, then I can say, okay, well, if I rearrange this, if I wanted to find the mass that was used in this experiment, I wasn't given the mass that was used in the experiment, but assuming the planet was done on Earth, so I know the value of g, I can say that's fine. I'll rearrange this, take the g down here, and then I'll have m equals gradient over g. So if I take the gradient, and if I take the gradient, divide it by 9.8, or whatever the exam version of g is inside the front cover of the paper one, mass equals gradient, and I can find the mass that was used in this experiment, whatever it may be. Now, what I've just discussed is really my attempted briefing and guide for doing question 13 of the 2018 paper. Now, I've done it in a subtly different way, but not that subtle. So I'd like you to now have a go at doing question 13 of the 2018 paper and go back through the video if you've got any thoughts on the gradient or other bits. Use the video to help you. Okay. Now, my advice, this is kind of parental advice that I had when I was young, is these questions have a lot of words in the question. So for those of us that are not super commanders of the English language, I would suggest go slow. Try to be very methodical with the question. There's a lot to read. Okay, so those of you who are not good at the Old England, think. Read the whole question through slowly, twice, before you set off. Don't make any assumptions and be very, very patient. Okay, there's a lot of marks on these and they're fairly straightforward to pick up if you're careful. So go very carefully, slowly, and see what you can do. And if you go through your 2018 paper, I would appreciate it if you could send an image of your graph and your working. So think about how you're going to do it. I really need to see an image so that I can give you genuine feedback and look at your graphing plots and the details of your graph. Okay, so we can't just kind of discuss what you've got to. Send me an image of your graph and an image of your working. So maybe if you do the working on one sheet of A4 and you do your graph on another sheet on a sheet of the graph paper A4, and then you send me 2 images and I can see what's going on. If you do 2018 nicely, then question 13, 2018, if that goes well, I'm hoping to get on to do question 15 of the 2017 paper. And that's the plan for today. Okay, take care.